Hello everyone. Today I'm going to discuss about physical chemistry as part of our uh, curriculum for second BSc students. So in this first I begin with the introduction of solutions and then Raoult's law and its limitations, then colligative properties, distillations and different types of distillations like fractional distillation and steam distillation, and azeotropes or azeotropic mixtures. So solutions of liquids and liquids are what is solution? Solution is a homogeneous mixture of two or more substances, the composition which may vary in certain limits. The solution consisting two components is called binary solution. The component which is present in large quantity is called solvent, and the compound which is in small quantity is called solute. So types of solutions, there are three type of matter. Uh, One is gas and one is liquid, one is solid, which which may behave either solvent or solute. Depending on the state of the solute and solvent, there are different types of binary solutions. For gas and gas, examples is air, cooking gas, humidity, etc. Gas and liquid, soda water, uh, and gas and solid, hydrogen in palladium, and the liquid and solid, mercury in zinc amalgam. Another example, moisture in air, solid and liquid, salt in water, sugar in water, and solid and gas, smoke. So we have different types of examples for solute and solvent. So then one more thing, what is vapor pressure? I will discuss later. So the solutions of liquids in liquids. Uh, Today we are going to discuss about this one and this solutions of liquids and liquids. Depending upon the relative solubility of liquid in another liquid, the binary liquid mixtures means two components. One is solute and another one solvent. It is divided into three types. First one is completely miscible. Second one is partially miscible, and third one is immiscible. So what is completely miscible? Miscible means when the two liquids are completely soluble in each other in all portions is called as completely miscible liquids. These involve of, of both of which are either one is polar and the other one is non-polar. Chemically like substances form completely miscible solutions. Examples: benzene in toluene, alcohol in water. Now let's go to the second one, partially miscible liquids. When a liquid is soluble in another liquid at certain extent, means it's not completely solved or it's not completely soluble or it's not completely insoluble. At certain extent only it is soluble. So it is called partially miscible liquids. So the resulting mixture separates into two layers of each being of solution one and another. So in this type, one of the liquid is polar, the other one is non-polar. Examples: phenol in water, ether in water, nicotine in water, etc. The third one is immiscible liquids. So when two liquids do not mix at a is called immiscible liquids. So in this also, one is polar, the other one is non-polar. Examples: carbon tetrachloride, CCl4 in water, benzene in alcohol, benzene in water, amyl in water, water mercury. So we have various numbers of examples. Now, so again, solutions are classified into two types. One is ideal solutions, the other one is non-ideal solutions. So ideal solutions. Solutions in which solute, suppose solute is A and solvent is B. So when solutions in which solute means A and solvent BB. Interactions are almost similar to solute solvent means AB is called ideal solutions. It is very important to note that in very dilution state, all solutions should tend to behave ideal manner. So there are some certain characteristics for ideal solutions. So change in volume. That means delta V should not be on mixing should be zero. Volume change on mixing should be zero and should not be greater than or minus zero. So it means that V solvent plus V solute equal to V solution. Means solvent plus solute equal to solution. So R in simple words, delta V mixing equal to zero. The same way, heat change on mixing means enthalpy uh, on mixing should be zero. So it means heat neither absorbed nor evolved. So change in enthalpy is zero. The third one, and two components should not react each other. That means no chemical reaction should takes between solute and solvent. So suppose we take ammonia plus hydrochloride, should not form NH4Cl, ammonium chloride. So likewise, it should not takes place reaction from solute to solvent. So there are likewise, and then it should obey Raoult's law. Raoult's law, ideal solution should obey Raoult's law. And then the activities of the components should be equal to their mole fractions. Then no dissociation or association takes place here. There should not be any association or dissociation during in ideal solutions. And then it should not form any azotrope mixtures. So the examples are benzene and toluene, hexane and heptane, ethyl bromide and ethyl iodide, chlorobenzene and bromobenzene. So a number of examples are there. And then CCl4 and silica tetrachloride. So all dilute solutions. So many examples are there. Now let's go to the Raoult's law. Raoult's law. According to Raoult's law, it is according to Raoult's law, the partial pressure of each component in the solution at a given temperature is equal to mole fraction of the component in the solution multiplied by the vapor pressure of the component in the pure state at the same temperature. Means the partial pressure of the each component is equal to mole fraction of the component multiplied by vapor pressure of the component in pure state at same temperature. Let us take a binary solution of two components A and B. The total vapor pressure means P having Na moles of volatile liquid A and Nb moles of volatile liquid B. So PA and PB are the partial pressure of two liquids. So according to Raoult's law, the vapor pressure is PS is directly proportional to mole fraction. So mathematically, P solution directly proportional to solvents. So here P solution equal to K into X solvent. Here PS equal to P equal to K. Means P solution equal to P solvent into X solvent. So this is the graphical representation of Raoult's law. So plot versus P solution versus mole fraction. It is a linear function. Y equal to mx plus b. So it's a straight line with a slope equal to most the P solution directly proportional to X solvent. Vapor and vapor pressure. Vapor is the liquid molecule in a gas form over the liquid surface. So remove the liquid and then we have a gas. So vapor pressure at a particular temperature, the pressure acted over the substance at which the vapors are formed, then the pressure is called vapor pressure. The formation of vapor always a dynamic equilibrium. So let us take an example of initial and final. So in a closed container at constant temperature, an equilibrium of vapor pressure is established. Here, dynamic equilibrium established. The picture on the left indicates vapor molecules leave solvent to dilute solutions. The solute decreases and the solvent molecules per unit volume, lowering the tendency for the molecules to escape the vapor. The vapor pressure of the solutions in solution in pure states is much different. Vapor pressure of the pure solvent is decreased when non-volatile particles are dissolved in it. So limitations. There are certain limitations for Raoult's law. The solutions which obey Raoult's law is called ideal solutions. However, in certain times, it's this one Raoult's law. However, the real solutions means non-ideal solutions deviates from Raoult's law. Raoult's law is only applicable to dilute or less concentrated solutions. So here, in this case, AA represents solvent-solvent molecules. AB represents solute-solvent molecules. Gamma is the attractive force between molecules. Then gamma AA equal to gamma AB for ideal solutions. This one, H greater than or less than means positive or negative deviations. Negative and positive deviations. In positive deviation, and the cohesive forces become dominant over adhesive ones. In negative deviations, the vapor pressure of the mixture is lower than expected from Raoult's law. Then it is said to be negative deviation. Negative deviation, adhesive forces between like molecules is dominant over the cohesive forces between the molecules. If the vapor pressure of the mixture is higher than the Raoult's law, then it is called positive deviation. So another important concept is colligative properties. Colligative properties are those properties observed when the non-volatile solute particles are dissolved in the dilute solutions. Colligative properties depend on the number of particles. How many particles, solute particles are present as well as the solvent, and it does not depend on the nature of the solvent. But these properties are independent, means nature of the substance and the chemical reactivity of the substance. So it is dependent on the number of the particles, not dependent on the nature of the substance. There are, when the solute is dissolved in dilute solutions, the following properties are exhibited. So here one more is missing, osmotic pressure. So first one is lowering of vapor pressure. The second one is elevation of boiling point. Third one is depletion of freezing point. The fourth one is osmotic pressure. Now here, if you see the circle, vapor pressure and boiling point and freezing point. These are vapor pressure is not a colligative property. Boiling point also not a colligative property. Also freezing point means individually they are not colligative properties, but lowering of vapor pressure is a colligative property. Elevation of boiling point also colligative property. The first one is lowering of vapor pressure, means the vapor pressure of pure solvent is decreased when non-volatile solvent is dissolved on it in it. What happens when a pure solvent is there, vapor pressure, certain vapor pressure is there. So on the top, if we add some non-volatile solvent, so what will happen? It block the surface. So the vapor pressure of the solvent is decreased. So P is the vapor pressure of the pure solvent, PS is the vapor pressure of the solution. Then the lowering of vapor pressure equal delta P equal to P minus PS, where P is greater than PS. The relative lowering of vapor pressure equal to P minus PS by P. The relative lowering of vapor pressure is relative to the vapor pressure of the pure solvent, referred as relative to the relative lowering vapor pressure. Then relative lowering vapor pressure equal to P minus PS, P minus PS by P. Then if you mathematically P minus PS by P equal to mole fraction of the solute X solute, P minus PS by P equal to N by small n plus capital N, where small n is so small n and capital N are the solute and solvent. So relative lowering of the vapor pressure refers to all values relative to the vapor pressure of the pure solvent. Pure molecules leave surface, lowering the vapor pressure. Solvents with non-volatile. Pure solvent, it won't block. So vapor pressure is higher than non-volatile solute. Next one is boiling point elevation. Boiling occurs when the vapor pressure of the liquid equals to the atmospheric pressure. But since the vapor pressure of the solution is always lower than the pure solvent, more heat will be needed to boil the liquid. So here the pressure of the atmosphere using on the liquid, here the pressure of the evaporated vapor means the vapor pressure. So for example, if you take pure solvent and solution, so pure solvent boiling point temperature TB, for here boiling temperature T. So T is greater than TB. So T with change in this one TB equal to T minus TB. So boiling point elevation, delta TB equal to T1 minus TB. Here if you see pure one is T1 and then this change is TB here. So the quantitative relationship which describes the behavior look like so delta TB equal to KBM. So delta TB is the change in the boiling point, where Kb equal to molar boiling point constant, which is a property of the solvent. So where M equal to molarity of the solute in the solution. Now the next third point is freezing point depression. Freezing point depression is colligative property, but freezing point is not a colligative property. Remember that one. The freezing point depression is a colligative property observed in solutions that results the introduction of solute molecules to a solvent. Freezing point of solutions are always lower than the pure solvent, which is directly proportional to molarity of the solute. Here solvent only, here solvent solute plus solvent, which is the entropy. So when salt is added to water, the water freezes before the freezing point. As a result, freezing point is depressed. So it is more common in chemical labs. For cooling purpose, they add some salt. Salt water has a lower vapor pressure than pure water. So the freezing point is pure solvent versus solvent solution. Delta TF equal to TF minus T. So here mathematically delta TF equal to KFM. So TF is the freezing point of the depression. KF equal to molar freezing point constant. Value depend on the solvent. M equal to molarity of solute in the solutions. Now, next important concept is distillation and azeotropic mixture. This is a very important topic. Distillation is a physical method of separating mixtures depending on the difference in the boiling point of the component substances. Distillation is the process of purification of compounds based on their volatility. This is a physical separation process, but it's not a chemical reaction. And then the working principle of distillation is to heat the mixture at a specific temperature and collect the hot vapors and condense them back to liquid form. So types of distillations, there are several types of distillation depending on the procedure and instrument setup. Each distillation type used for the purification having different properties. First one is simple distillation, fractional distillation, steam distillation, vacuum distillation. So simple distillation is practiced in for a mixture in which the boiling point of the compounds differ by at least 70 degrees. In common laboratories, we use this one. Simple distillation mixture is heated to change the most volatile component to liquid vapor. Vapor rises and passes through the condenser. Here, if we heat and vapor rises and passes through the condenser is having a cooling system, a cooling water supply, and then it will condense and collect into the round bottom or beaker. So double distillation is the process of repeating distillation collective order to enhance the purity. Here we monitor with the thermometer. This is more common in chemical laboratories. So another important point is steam distillation is used for the purification of mixtures in which the components are temperature or heat sensitive. For example, organic compounds. So in the instrument setup, steam is introduced by heating water, which allows them into compounds to boil at a lower temperature. So this way, temperature sensitive compounds are separated before decomposition. So the vapors are collected and condensed through cooling system, condensed and into the same way through distillation pipes. So the resultant liquid consists two phases: water compound and then purified using scintillation. Actually, here we are using steam. So the compound, resulted compound comes with along with water. So mostly in essential oil industry, they use this steam distillations. Perfume industry. So steam distillation practice large scale preparation for essential oil. The next one is a fractional distillation. These mixtures in which boiling point of the compounds nearly similar or differs by 25 degrees and cannot be separated by steam distillation, simple distillation. So we use a fractional column where the plates are arranged and the compound with least boiling points are collected. Here, in normal condensers, we don't have any plates, but in the steam distillations, we use some plates. And then same process, vapor, after heating vapor rises and then it goes to the column. And so here cooling and it will condense and liquid will be collected. Now, azotrope. Now next point is azotrope. Azotrope means it is a mixture of two or more liquids whose proportions cannot be separated by simple distillations. An isotope is formed when a liquid and vapor compositions are same. When the isotope is boiled, the vapor is same portions of the combining as the unboiled mixture. The name comes from Greek word boiling without changing. So isotope, when the isotopic composition has reached, distillation cannot separate the two liquids. Isotopes form only when a mixture deviates from Raoult's law. Means only real solutions only form isotopes. Means non-ideal solutions. So there are two types of isotopes. One is a positive isotope, and the other one is negative isotope. Each isotope have a characteristic boiling point. The boiling point of isotope is either less than the boiling point of temperature or remove constraint, or greater than the boiling point of the constraint. So if it is greater than, less than means it is a positive isotope. If it is greater means it is a negative isotope. So for example, a positive isotope is ethanol water. 95.63% of ethanol and 4.37% of water boils at 78.2 means positive means positive means what? Isotope is either less than the boiling point. So it is less than this one. So say here another one is ethanol boils at 78.4, water boils at 100. So what the isotope boils at 78.2, which is lower than the either of the constants. Indeed, 78.2 is the minimum temperature at which ethanol water solution can boil at the atmospheric pressure. The positive isotopes are also called minimum boiling mixtures or pressure maximum isotopes. In general, negative isotopes boils at a higher temperature than the ratio of the constants. Negative isotopes are called maximum boiling mixtures or pressure minimum isotopes. Negative isotope examples are hydrochloric acid, water, HCl water systems. So HCl boils at -84 and water boils at 100 degrees, but the isotope boils at 110, which is greater than, higher than either of the constraints. So maximum temperature at which hydrochloric acid solution can boil at 100 degrees or 110 degrees. So isotropic distillation, it involves the addition of new component called either a trainer to the original mixture to form isotrope. So what is a trainer? How do they work? An trainer is an agent which affects the volatile of the one of the isotropic combining with. combinings more than one another. So if the one of the combinings are more volatile, then it can be separated by distillation. So the use of ethanol in the isotropic ethanol water isotope can be separated by adding an ethanol cyclohexane. So when cyclohexane added, it engages all of the water to form isotope and then boiled isotope evaporating and leaving the desired ethanol free water. Actually, we here there is a spelling mistake. Benzene. So benzene is having some toxic effect. So that's why nowadays cyclohexanes are using it. Thank you.